and hi everyone. Today we'll try to understand the most important algorithm in ANN, what do you call it as backpropagation algorithm. Let's first understand how the backpropagation algorithm is going to work. What is the need of backpropagation algorithm? We'll try to understand the working of this particular algorithm with the help of an example. In this particular algorithm, we are going to train our network by giving input pattern and wherein the output is known to us. So in this particular algorithm, we are going to consider three main layers over here called as an input layer, which is represented by I1 and I2 having two nodes. Then we have a hidden layer wherein you have nodes called H1 and H2. And then you have an output layer wherein the nodes are represented by O1 and O2. Now, in this particular algorithm, we are given with the input. We are going to provide this input to our network, and then we are known with the output. So, by giving these various inputs, we want to check whether our network is going to provide us the desired result which is given over here or not. So, we are going to see whether the network or the model that is designed is going to give us this particular result or not. In case the result is varying, then what we need to do is we need to go back and then we try to do some processing over there. So whatever input is given over there, we are going to process this input by means of providing some weights over there along with the bias, and then considering the input at H1, that is hidden layer, and then again we are going to work with some of the weights over here along with the bias. Then it becomes an input to your output layer, and then we do the processing at output layer so that you get some kind of output over here. Now, a question that comes is, why do we need backpropagation algorithm? So whenever we are designing any kind of neural network, in the beginning, we are going to consider some of the weights over here. And these weights, which you have taken over here called W1, W2, W3, W4, W5, 6, 7, 8, and so on, we have taken the values for that at random in the initial stage. As we know, we are not the superhuman over here to predict the exact values. So what we are going to do, by taking some random weights over here, we are going to do the processing and then we are going to generate some output. Our output will be compared with the target output. And if there is any difference, if there is any kind of error over there, or the difference between the target and the output generated by our model, then in that case, we are going to modify the weights that we have provided over here at the beginning. In that way, we are going to train our system so that we see in the final the target output and the desired and the output that we have generated is very near to each other and so on. So in this process, we may need to change these weights like W5, W6, W7, W8 along with W1, W2, W3, W4 for multiple number of times over there. So let's consider an example. This is what the ANN we are going to take, wherein you have two input nodes, two hidden nodes, and then hidden nodes, and then you have two nodes in the output called as O1, O2, and so on, along with bias 1, bias 2, and so on. So initially, the weights are considered as W1 with 0.15, W2 as 0.2, W3 as 0.25, W4 as 0.3, and so on. Similarly, W5, W6, W7, W8, along with bias 1 and bias 2 over there. Now, the input that we are going to provide is 0.05 and 0.1. And what we expect from this particular network is the output as 0.01 over here and 0.99 over here. So now, how is that we are going to process this input, and then how is that we are going to generate the output? So what is that we need to do first over here is we need to check what is the input that we are going to get at H1. And then we are going to make use of some activation function at H1, and then you will get some input, that is output of H1, which will be given to the input of O1 and so on. So when you are going to provide the input to O1, the output of H1 will be again multiplied with the weights over here, and then the output over here is calculated, which becomes an input for your O1. Now again at O1, you are going to make use of some activation function over there so that you get some result over here. So how is that we are going to do? So to start with, initially we are going to find out what is the input at H1. So the way to calculate is the input at H1, otherwise you can also call it as net H1. So which will be equal to W1 multiplied with I1. So this input you are going to multiply with W1 plus W2 multiplied with I2, W2 multiplied with I2 along with the bias b1 multiplied with 1 and so on, like so this is b1 multiplied with 1 and so on. So that becomes the net input at H1 and so on. You call it as net H1 over there. So if I consider the value of W1 at 0.15 and then by replacing the values for all this, I'm going to get the input, that is a net input at H1, which is 0.3775 and so on. So this is going to be the input at H1. Now what I'll do is at H1, I'll make use of an activation function which is called a sigmoid function, and then I'll try to generate the output of H1. And then this output of H1, I'm going to process with the help of weights over here. That becomes the input for O1 and so on. So what is the output of H1 now? The output of H1 after you apply the activation function, which is sigmoid function, and the sigmoid function over there is 1 upon 1 plus e to the power x, where x over here is nothing but the input that you are receiving and so on. So here we say 1 upon 1 plus e to the power minus net H1. So when you calculate by replacing the values over here, you are going to get the output for this, which is output of H1 at 0.593269992 and so on. Now similar way, we are going to perform the calculation for input at H2 and output of H2. So how is that we are going to do now? Input at H2 equals to W3 multiplied with I1 plus W4 multiplied with I2 plus B1 into 1. Similarly, so when you calculate the value for this, after replacing this value of W3, I1 and so on, you are going to get the output for this as 0.3925 and so on. Now this becomes the input of H2, and then when you apply the sigmoid function over there, that becomes the output of H2. Now when I apply this, I'm going to get the value for that as 0.596874 and so on. So now I got the input at H1, I know the input at H2, I know the output of H1, output of H2 and so on. Now I need to provide this output to the node at O1 and O2. So in that case, what I'll do, input for O1, I can write it as, or I can call it as net O1, which is out of H1 multiplied with W5 plus out of H2 multiplied with W6 plus B2 into 1, that is bias 2 into 1 and so on. So when you replace the values for this, or when you go with the values of various variables that you have taken over here, or the weights that you have taken over here, then the output over here is going to be 1.105905 and so on. Now this is the input at O1. Now if you want to get the output or calculate the output at O1, then you need to apply the activation function at out1, which is 1 upon 1 plus e to the power x. So you can just calculate this as 1 upon 1 plus e to the power minus this value and so on. So in that case, you are going to get it as 0.751365 and so on. So similar to the way we calculated input for O1 and output of O1, we can also calculate the same for output of O2. So just by replacing over here W7 with H2, W8 with H2 and B2 into 1 and so on, and then calculating with the help of this activation function, you are going to get the output of O2 as 0.7729 and so on. So the output of O1 is 1.10, sorry, the output of O1 is 0.7513 and the output of O2 is 0.7729 and so on. Now that means the output that we were in need over here was 0.01 and over here we were in need of 0.99. But what is that we have generated over here? The output of the model that we have designed, we got it at 0.75 over here and 0.77 over there in our O2. That means there is an amount of difference between these two values, the one which is required and the one which is generated. So you are going to calculate the error for O1 or error at O1, you can say error at O2 and so on. So in order to calculate that, you can make use of 1 by 2 into target minus output whole square. So if you replace the value of target, which is 0.01, this is what exactly we need, and what we generated is this. If you calculate this, you are going to get the error over there at O1 at 0.274811 and so on. Similarly, if you calculate this for O2, you are going to get error at O2 at 0.02356 and so on. Now the total error that we got is error 1 plus error 2, which is going to be 0.2983 and so on. Now, because there is a difference in the output that we generated and the output that is required, what we need to do is we are supposed to go back and then we are supposed to change the weights at this particular level. That is, first we can change W5, then W6, W7, W8, and similarly, you can also change the weights over here at W1, W2, W3, W4, and so on. So, how is that we are going to do this now? So what is that we need to do now? With respect to the total error that we got, how is that we are going to change the weight called W5? So we need to perform here some partial differentiation wherein we are supposed to calculate partial differentiation of E total with respect to W5 you want to calculate, so that you can get a value which can be used to change the value for W5 and so on. So this, when you apply the chain rule, can be written as E total by out 1 multiplied by E total upon net 1 multiplied by net 1 upon W5 and so on. So now if I consider this as 1, 2, 3, when I calculate the values for this and when I multiply, I'm going to get the value of E total with respect to W5 and so on. Now, how is that we are going to calculate the value for E total upon out O1? That is error total upon or with respect to out O1. So, partial differentiation of E total with respect to out O1 we want to calculate. And this, when you calculate, we get it as out O1 minus target O1 and so on. Now, the question that comes is, how is that this we could generate with the help of this? So a small explanation over here is given to you in order to understand this particular step with clarity. So E total, as we know, is the total error, which is nothing but your target O1 minus out O1 whole square plus 1 by 2 into target O2 minus out O2 whole square and so on. So this is nothing but this is our E total. Now E total with respect to out O1, if you want to find out over here, the partial differentiation of E total with respect to out O1, if you are going to calculate, we know that if it is a y square, I can write y square as 2 into y to the power 2 minus 1 over there. So by considering this, I can write it as 2 into 1 upon 2 target O1 minus out O1, 2 minus 1 over here. Now, if I consider the internal differentiation of this, I can write it as out O1 minus, target O1 minus out O1 into, with respect to out O1, if I calculate, I will get it as target O1 minus out O1 upon out O1 and so on. Now, when I do this partial differentiation or differentiation with the help of out O1, I'll get it as target O1 minus out O1, and this being constant. Okay, so I will write it as 0 minus 1 over here. So this I can write it as minus target O1 minus out O1 over there, which I can write it as out O1 minus target O1. So E total upon, that is partial differentiation of E total with respect to out O1. You can write it as out O1 minus target O1. So now if I replace the value of out O1, as we know the value of out O1, we calculated over here. Out O1 is nothing but this is the value. So if you try to replace the value over here, this is 0.75136 minus the target, which is 0.01. You are going to get here 0.7413 and so on. So this is how we could calculate E total upon out O1. Now the next step that we need to do is partial derivative of out O1 with respect to net O1 we are supposed to calculate. So out O1 with respect to net O1, we can write it as out O1 into 1 minus out O1. Now again a question, how is that we have generated this from this? So for that what you can do is, if you consider f of x equals to 1 upon 1 plus e to the power minus x, then you can write this as 1 upon 1 plus 1 upon e to the power x, which can be written as e to the power x plus 1 plus e to the power x. If I go with the quotient rule over here, I can write it as u dash v minus v dash u upon v square. So if I'm going to replace the values over here, u dash v, I can write it as e to the power x into 1 plus e to the power x. If I consider this as u and v, so I can write it as e to the power x into 1 plus e to the power x minus v dash. When you take with respect to e to the power x, that is when you go with respect to dx, then you can write it as e to the power x into e to the power x upon 1 plus e to the power x whole square. So now this you can write it as ex e to the power x plus e to the power 2x minus e to the power 2x over here. Now from this you can write it as e to the power x upon 1 plus e to the power x whole square. So when you cancel this, okay, and then from this I can write it as, if I consider this as fx, then I can write it as fx into 1 upon 1 plus e to the power x. Now this I can write it as fx into 1 minus fx. Now 1 minus fx can be written in this fashion, 1 minus fx. If you go with this, wherein you know the value of fx, so if you replace these values over here, and then when you cancel this, you are going to get it as 1 upon 1 plus ex, so which is nothing but this. So this I can write it as 1 minus fx, and the total thing that you get over here is fx into 1 minus fx. Now with this, I can write over here out O1 with respect to net O1, partial derivative of this with respect to net O1, I can write it as out O1 into 1 minus out O1. By replacing the values over here, I'm going to get the value for this as 0.18. So the second step over here is completed. The first step has generated this result 0.74. The second has generated the result as 0.18. And the last step, net O1 with respect to W5, if you calculate, we know partial derivative of net O1 with respect to W5, you can just write it as out H1. That is because net O1 is nothing but W5 into H1 plus this. We have already performed the calculation for this. Now, if you perform the partial differentiation with respect to W5, then you are going to get this as out H1, with the value of which is 0.5932. Now you got the value for your three steps that you wanted, 1, 2, 3. And if you try to calculate or multiply all the values that you got, you are going to get the output over here at 0.08216 over there. Now you need to find what is the new value that you want to have for W5. So you can write W5 star, you can write new W5 and so on, which will be equal to W5 minus alpha. What is alpha over here is, it is a learning rate, the value of which you can take it from 0 to 1 and so on, multiplied by the value that you have generated by calculating the partial differentiation of E total with respect to W5. So if I replace the values over here, W5 is 0.4 minus The alpha rate, which I have the alpha, which is learning rate, I have considered it as 0.6. You take it at 0.3 or 4 accordingly, multiplied the value that you got over here, then you will get the final output at 0.3506 and so on. That means the new value of W5, which was initially zero point 0.4, has to be now replaced with 0.3506. So that means what we have done, by coming back over here, we have calculated the new value for W5. Similarly, you need to do for W6. Similarly, you need to do for W7. And similarly, you have to do it for W8. Now that we have modified the weights at O1 and O2, what we need to do is we need to go back to the hidden layer, and then we need to see how we can modify W1, W2, W3, W4 and so on. So in order to do this, we need to calculate the partial derivative of E total with respect to W1. And then this I can write in this fashion by applying the chain rule. Partial derivative of E total upon out H1 into out H1 upon net H1 and net H1 upon W1 and so on. This kind of applying of chain rule we have already done in our previous exercise. So now we need to find out the value for this, the value for this, the value for this. When you multiply this, you are going to get the value for this and so on. Now, partial derivative of E total, that is error total, with respect to out 1, out H1, we can write it as, we know the complete or total error is nothing but EO1 plus EO2 and so on. So this I can write it as partial derivative of EO1 upon out H1 plus EO2 upon out H1 and so on. Now this EO1 upon out H1, I can write it as EO1 upon net O1. Again, I am applying a chain rule over here, and net O1 upon out H1 and so on. And similarly, I can write this as EO2 upon net O2, net O2 upon out H1 and so on. Now this again, EO1 with respect to net O1, I can again apply a chain rule over here, and I can write it as EO1 upon out O1 multiplied with out O1 upon net O1 and so on. And this value, that is the partial derivative of net O1 with respect to out H1, I can just write it as W5. Now we need to understand here how is that we are going to write this as W5. Net O1 upon out H1. So here you need to consider these two things. What is the input that you are getting on, that is, what is the input or where from you are going to get the input for O1? It is from H1. And what is that which is connecting H1 and O1 nodes? It is nothing but W5. So this particular step I will replace with W5, and similarly net O2 upon out H1 I am going to replace it. Because this is getting connected with W7, I'm going to replace this particular value with W7 and so on. Now this particular step I can write it as EO1 upon out O1 multiplied with out O1 upon net O1 multiplied by W5. In the similar way, you will do this for EO2 and so on. Now this, when I calculate, you will get it as EO1 upon out H1, out 1 multiplied by out O1 upon net O1. Now, this you can write again as EO1 upon out H1, out O1 is equal to, you can write this as out O1 minus target O1 multiplied by, this I can write it as out O1 into 1 minus out O1. These two steps we have already performed in our previous exercise over there. Now, if you try to replace the value of this, which is 0.7413, multiplied by the value of this, which is 0.18, and then you have to multiply these two with the help of W5. So the net value that you get after you calculate this is 0.055399 and so on. Now, similarly, you need to calculate this for EO2 upon out O2 multiplied by out O2 upon net O2 multiplied by W7. So when you perform the calculation over here, you are going to get the value for that as minus 0.019 and so on. So then if I calculate this E total upon out H1, I'm going to get the value for this as, here we have to perform, we are calculating this. So you have to perform addition of this plus addition of this. So when I'm going to do that, I'm going to get it as 0.055399 plus the value of this, which I said is 0.019049. So I'm going to get the value for this as 0.036. So what we are trying to do over here is we are trying to find out the value of E total upon out H1, partial derivative of partial differentiation of E total with respect to out H1. So when you want to calculate this, we can write this E total as EO1 plus EO2. And this, when you apply a chain rule, you can write it in this fashion. Again, when for this, if you are applying a chain rule, you can write it in this fashion. And this you can take it as W5. Similarly, you need to do the calculation for EO2 upon out H1. So then the final result that you get for partial differentiation of E total with respect to H1, out H1, you will get it as 0.036. Now you go for the next step, wherein you are going to calculate partial differentiation of out H1 with respect to net H1. So this already we have calculated in the previous step, and this can be written as out H1 into 1 minus out H1. And then when you replace the values for this, you will get it as 0.24130. And similarly, partial differentiation of net H1 with respect to W1, you can write it as net H1 upon W1, which can be written as net H1 can be written as W1 into X1 plus W2 into X2 and so on. With respect to W1, when you calculate, you will get it as X1. That is nothing but your input 1, which is 0.05, the value of I1, which is 0.05. Now, if you try to replace these values and then try to multiply the value for the first step and the second and the third, then you are going to get the output over here for this as that is partial differentiation of E total with respect to W1, you will get it as 0.000438 and so on. Now, once you get this value, then you can calculate the new value of W1 with the formula saying existing value minus the learning rate into partial differentiation of E total with respect to W1. And then when you try to replace the value, you will get the final value at 0.14973. So this is the new value for the weight called W1. So this is how you are going to calculate W1. And once you know how to calculate W1, you can easily calculate weight 2. You can calculate the value for weight 3, weight 4, and so on. So if you like this video, then you can share the video and subscribe to my channel. Thank you.